Good afternoon, class. And today we're going to be talking about evaluating a definite integral as a limit. Let me go ahead and put that as our title here. Evaluating a definite integral as a limit. Now this is really where we're going to start seeing the crossover between integrals and between the sigma notation that we've been doing. So yesterday we were talking about what happens when we take sigma notation and the ends that are associated with, so those intervals, and we make those intervals smaller and smaller and smaller. And so the number of intervals is going to grow and grow and grow until eventually the number of intervals is going to be infinity. So if I'm starting off with a function, say my function f of x is going to be equal to 2x, simple function, and I'm going to look at it over the interval -2, 1. So I'm going to start off just so that I understand what is going on, as always, and I encourage you guys to do this as well. Anytime you see a function or you're given a problem like this, is just to go ahead and sketch it out. So if I sketch this one out, 1, 2, 3, and it goes down a little bit further, 4, 1, 2. So here I've just got, this is a linear function, so it's a line with a slope of 2. So there's a point there, and there's a point down there, and the function kind of goes like that, and it keeps going. But since I'm just looking at it over this interval, this is the important stuff right here. Now if I'm trying to find the area between this function and the x-axis right here, then I know that I'm looking at this shaded area right here and the shaded area right here. Now if the shaded area is above the x-axis, then it's going to be a positive. It's going to have a positive value. And if the shaded area is below the x-axis, then it's going to have a negative value. So this is going to be positive and this stuff is going to be negative. Now that'll come into play a little bit later, but right now all you need to know is, let's take a look. The positive section is much smaller than this negative section, so when we come up with our total area, we know it's going to end up being negative, right? Because there's a larger negative section than there is a positive section. So let's try to find this area using our limits as n goes to infinity. So of course, if we start chunking this up into rectangle intervals like this, and say our intervals look like this, no matter how wide our n is going to be, remember, I'm just sort of drawing this out so that when I'm doing my sigma notation later, it just makes a little bit more sense. It doesn't matter the number of intervals I have now because they're going to go to infinity anyway. So the two things that I need to find, are going to be this delta x sub I, we learned this yesterday, is going to be equal to delta x, and the equation for that is b minus a divided by n. And so here, b minus a, this is our interval. So our interval is a comma b. And so delta x is going to be 1 minus -2 over n. And so then this is just going to be equal to 3n, or 3 divided by n, right here. Let's remember that, and then move on to our next important piece is going to be c sub I. Now remember, if we're using the right endpoint of each subinterval, then c sub I is just this equation, a plus I times delta x. And remember, a is just part of our interval here. So a is -2, that's what was given to us, plus I times delta x, and we just calculated our delta x right here, which is going to be 3 divided by n. So then I can say my ci is going to be -2 plus 3I divided by n. So now I've got the two important pieces of information, and I can start figuring out what the area under this curve is. So writing this into sigma notation, we should be pretty comfortable with this by now. So the limit as my delta goes towards 0 of sigma n, I is equal to 1. Then I've got the height of my rectangles, which is going to be f of c sub I, and then my width of my rectangles is going to be delta x sub I. This is sort of the definition. Now if I'm going to rewrite it with instead of deltas going towards 0, if I want to say n towards infinity, then I can say this is just going to be equal to a limit as n goes towards infinity, sigma, and I'm going from I is equal to 1 to n, f of c sub I delta x. Now I've got my I've got my c sub I right here, and I've got my delta x. So now all I need to do is just sort of plug these things in. F of c sub I, remember my original function is right here. F of x is equal to 2x. So my limit as n goes towards infinity, I'm just going to start plugging this in. So f is 2x, but I'm not finding f of x, I'm finding f of c sub I. So I'm just going to take this c sub I and replace it where all the x's are. So this first section is going to be, instead of 2x, it's going to be 2 times negative 2 plus 3I divided by n. And then my delta x I've got right here, calculated it up above, it's just going to be 3 divided by n. Now I'm going to simplify this. First thing I notice is I've got this n, and I've actually got this 2 out front, so I'm going to combine them and pull them out front. So 2 times 3 is going to be 6, 6 divided by n. And remember, n is it's a constant, right? It's eventually going to infinity, but it is just a constant. So I'm going to go ahead and pull it out. So my limit stays out front as n goes to infinity. And now I've got 6 divided by n, sigma, and then everything else inside, since I've got this 3 and I've got this 2 pulled out, all I'm left with is minus 2 plus 3I divided by n. So now, similar to what we did before, the problems we were solving before, I can break this up. You see I've got a term with a constant, and then I've got this other constant in an I. So I can break this problem up and just say the limit as n goes to infinity, 6 over n, and then I'm going to use big brackets, and I'm just going to say sigma minus 2 plus sigma 3I divided by n. And of course these are both n's, as I starts at 1 and goes towards n. Now using theorem 4.2 and replacing this stuff, replacing the i's and everything else, the constant as well, I get the same thing here, limit as n goes to infinity of 6 divided by n, and then just a constant just becomes c times n, and in this case my c is negative 2, so I just come up with negative 2 times n. And here I've got this 3 divided by n, that's a constant, and all I've got really here is my I. So I've got this 3 divided by n, and then replacing the I with the sigma notation from theorem 4.2, I can see that an I is n times n plus 1 divided by 2. And now I just need to simplify this a little bit. So next, I'm going to just focus on simplifying this section right here. Limit as n goes to infinity. My 6 divided by n is out front. And I end up with negative 2n comes along for the ride, plus this is going to be n squared plus n divided by 2. But then there's an n here, so these n's can cancel out. So then I just end up with 3 halves n, so 3 divided by 2 times n, plus 3 halves. Now let me switch over to a new sheet. Now once I get this far, I'm really, really close. I'm all just doing algebra at this point. So I'm just going to rewrite this function once more. So I have the limit as n goes to infinity. And now I can start distributing this 6 divided by n inside. And so 6 divided by n times negative 2n. So the n's cancel, and I just end up with negative 12. 6 divided by n times 3 over 2. So I just get 18 over 2. Once again, the n's cancel, I get plus 9. And then 6 divided by n times 3 halves. This is just going to be 9 divided by n. In this case, the n stays on the bottom. There's nothing to cancel it out with this constant term. Now as n is going to infinity, this is where this limit comes in. As n is going to infinity, this 9 divided by n, as n goes infinity, this just gets bigger and bigger and bigger. So it starts off with as n is 1, n is 10, n is 100, n is 1,000. So 9 divided by 1,000, very small number. 9 divided by 1,000,000, very small number. Effectively, this one just goes away. It goes towards 0. So all I'm left with is just negative 12 plus n, and this is going to be equal to negative 3. So this is the sigma notation way of solving this. Now if I wanted to write this exact same problem with definite integrals, this is where we're evaluating definite integrals, I would take my original function. So remember, my original function f of x is going to be equal to 2x, right? And we're looking at the interval negative 2 to 1. So if I wanted to write this in integral notation as a definite integral, this is how I would do it. So I say my integral from a to b, in this case a is negative 2 and b is 1, of f of x, in this case is 2x, then remember we've always got this dx out front that tells us what term we're taking the integral in relation to. So this is equal to this whole long string of limits and sigma notations all the way down, and it's going to be equal to negative 3, which is our answer that we got here. Now if you look at our original drawing here, our original plot, that's exactly what we found. So we had a very small positive portion, we had a larger negative portion, so the overall area ended up being negative, which is exactly what we saw. Fantastic. Now I'm going to draw a line here and sort of summarize this in math notation. So say we have an area bounded by a curve. Area bounded by curve and the x-axis. And just to sort of draw out a general form of this, we've got our y-axis, we've got our x-axis, and we've got some general curve in here. We have no idea. It's some function f of x. Okay? And we're looking at it on the interval from a to b. And so this is the area that we're looking at, everything in here. If we've got this, the general form of what we're doing and how we write this is we would just say the area is going to be equal to the definite integral from b to a f of x dx. This is incredibly, incredibly important. Put a box around this, make sure you notice this, make sure you have this memorized. The definite integral from b to a f of x dx. We're going to work with this a lot. This is so important. This is one of the fundamental theorems of calculus, okay? Right here. And it all stems from sigma notation as our intervals get smaller and smaller as our number of intervals goes towards infinity. We'll pick up here tomorrow. Get ready to get some practice in, guys.